Okay, my second example, we are now looking at when the acceleration is given in terms of velocity. So a particle slows down under the influence of retardation, which can be considered as negative acceleration in meters per second squared, which is proportional to the square of its speed in meters per second. Its initial speed is 20 meters per second, and its initial retardation is 20 meters per second squared. Find its velocity at time t seconds and its displacement when t equals 10 seconds. Alright, so there's some interesting language in here that we must first consider. So the first one we just mentioned is retardation, which, as I mentioned in the question, it's kind of like negative acceleration. But the other thing that's going on here is we're also talking about the speed. So retardation is slowing down. So if its velocity was negative and its acceleration was also negative, then what would happen is that object would just get faster and faster and faster, but in the negative direction. So if it's getting faster in the negative direction, then that's not retardation. So what we're going to assume here is that the speed, we're going to call this the velocity. Now it could be positive or negative. So I could do this two ways. I could have the velocity as a positive and the acceleration as a negative. So then they would be opposites and it would be slowing down. Or I could have the velocity as a negative and the acceleration as a positive. So then again, they would be opposites, which would cause the particle to slow down. I'm going to take the first obvious choice here. And for this question, I'm going to use velocity as a positive value and the acceleration as a negative value. Now, the other bit of language here is proportional. We've seen this when we did our work in differential equations. And that essentially means that the rate of change is multiplied by some constant scalar value. So in this case, we're going to say that the acceleration is equal to some multiple of the velocity squared. So we've got, it is proportional to the square of its speed. And because the acceleration we've decided is negative, I'm going to put a negative value out the front here. We also know that initially we know that time is 0. So at the very beginning, time is 0. The velocity is 20 and the acceleration is minus 20. Because again, for retardation, it's slowing down. So because this formula has a V and an A in it, and we've got V and A, then my first step is to use substitution to find K. So we're going to find K by substituting in A equals negative 20 and V equals positive 20, which gives negative 400K is equal to negative 20. So K must be equal to 1/20. So now I can rewrite my formula as acceleration is negative 1/20 V squared. Or acceleration is the same as the change in velocity with the change in time, which is equal to negative V squared over 20. And I've made this definition to write the acceleration as a rate of change because looking ahead at part A, that's exactly what I want to find is the velocity in terms of t. So I've brought a v and a t into this expression. Alright, so to solve this differential equation, this is a differential equation in terms of the dependent variable. So the first thing I do is flip it upside down. Then I'm going to find out what time is, and I'm going to use an integral of, I'm going to write this as negative 20v to the power of negative 2 of dv. And And I'm also going to use that trick of substituting in to get my rule in one step. So I'm going to say I want to find out what V is, and I'm going to use the initial V value of 20 and the initial T value of 0. So when I integrate, I'm going to get negative 20 times by add 1 to the power, which is V to the power of negative 1, and divide by that new power. Substitute in my terminals and put my plus 0 on the end. Now I'll ignore the plus 0 at the next step. This just gives me 20 V to the minus 1, still from V and 20, or I can say is 20 over V, from V to 20, and if I sub these values in, I get 20 over V, take away 1. So there's my rule for T with my constant of integration already calculated. Now obviously I don't want to know what T is, I want to know what V is, so a quick bit of rearranging, and I can write my rule for V as 20 over T plus 1. Okay, so I've got V now, which was part A completed, so it's velocity at time t seconds. We have done part A. My next thing is I want to find the displacement when t equals 10 seconds. Okay, so to find displacement, I need to bring x into this, and I know that velocity is dx dt. So what I need to do now is I need to find out what the integral of this expression is, and I want to find it at the point when t equals 10 seconds. So I want to find it at 10 seconds, and I know initially t is 0, and the displacement, we're going to also assume that at my starting point we have displacement equal to 0. But I can't really assume that, can I? Do I know that the displacement is 0 initially? I would have to know the initial value of the displacement before I can do that. So I'm going to maybe just have a little bit of a stop and a think here. I'm going to get rid of these terminals because I think I might have been jumping ahead, and I'm just going to integrate, and I'm going to reread the question. A particle slows down under the influence of retardation, which is proportional to the square of its speed. Its initial speed is 20 meters per second. Initial retardation is 20 meters per second. Find its velocity, its time t seconds, and its displacement. Now I am going to put that back in. We're going to assume that we want to find out how far it has travelled since it began. So I'm going to assume that its displacement is actually 0, and we're going to find out how far it has moved from where it started at t equals 0 seconds. Okay, so I need to anti-differentiate this expression, which gives me 20 log to the base e of t plus 1. And I need to go between 10 and 0, and I have my plus 0 on the end. And I can also say, because time is always greater than 0, what I can actually do is get rid of those modulus signs in here. If time's greater than 0, then that part will always be greater than 0. So we should be good. Okay, substitute in some values here, and I get 20 log to the base e of 11 minus 20 log to the base e of 1, which becomes 20 log e of 11 minus 20 times 0, because log to the base e of 1 is 0, which becomes 20 log to the base e of 11, or an approximate value of 47.96 meters from original position. Scroll up, position. And that's the end.